All right. Well, let's hope this works. All right, let me go through and see what, today's a review day, right? That's probably why I'm doing that. All right, let's find out what we're doing then. I'll minimize that thing. Oh, by the way, the video lessons have been updated, so they include all the way up through 4.3. You should desire to go look at those things. Those are the ones I make for the online class. Today is our review. All right. So our test is going to be over chapters 3 and 4. And so what we'll do today is we'll talk about what's going to be on the test. I haven't really made it up, so we can discuss what types of questions we can even put on it. So I will take notes just as you do. Why are they doing that? I don't know. Whatever. All right, there was a lot of terminology. I'm not so much interested in the terminology as your ability to work with things. So first of all, let's take a look at, can you tell me what a sample space is? If I give you, so let's start with sample space. That's the most basic thing to the discussion of probability. Can you tell me what a sample space would be? Let's do, give the sample space
Thank you. Thank you.
for a pair give the sample space for a pair of twin children. You should have four outcomes, four possibilities here, right? So, remember, I think we talked about, you can't have them both come out at the same time. So, one comes first. So we do it, boy, boy. What's next? Girl, girl, that's those, then boy, girl, or girl, boy, right? There's four of them. I don't know what letters you use, probably F and G are probably, let me see, female, F and M is probably good. So you got, well, I guess I just decided not to use the letters I thought I was going to use. So something like this would be completely adequate. So be able to identify sample spaces of various events. What's the sample space if you roll a die? What, yeah, one, and then the whole numbers 1 through 6, right? I can't think of anything. What else could we have happen here? Well, anyways, you might be asked to create a sample space. Something that you'll definitely have to look at a sample space first. Suppose you got a spinner game like this. What's the sample space on this one? Right, the whole number is 1, 3. So a lot of times, so you may be asked a sample space, but you also might be asked questions dealing with it. So I like to give these because it's easy to visualize these things. So imagine this is like a spinner game. So can you imagine that? I don't know if I need to draw that or not. Are you serious? Oh, there's my spinner. So you spin it one time. I'm gonna ask you several questions about what could possibly happen. So there'll be some straightforward ones like this, just how many odd numbers do we have listed there? Out of how many total? Right. You have to look out, if I give you one that has an odd number of things, it should, I've seen some spinners have an odd number of these. This is not always gonna be 50-50. This depends on how many there are total. So we see that the probability of an odd number. You have 4 odd numbers out of a total of 8. What numbers am I talking about here? 6, 7, and 8. When we say between in math, we include the ends as well, so 6 and 8 are actually included. Yes. This would be a horrible review if it doesn't, there's no sound. Just tell me, yes, of course I would, oh, look there, I see I'm talking on it, okay, good. Between 6 and 8, so this is the probability of getting either a 6, a 7, or an 8. So we have 3 out of 8 total for that. This one's a combo one. Remember, the 2 most important words when it comes to these things are for and pan. They have specific usages.
That's to be less than one. 70.
Well, we,
In math, between is that. That's correct. It doesn't do anything, we don't know why it is. But I mean, well, just. It doesn't look like it went over so well. It's 6 out of 8. Let's take a look at what we have here. I'm gonna look at the odd numbers. Which ones are the odd numbers here? 1, 3, 5, and 7. So there's 4. Right? What else then? Between 6 and 8, we have
6 and 8.
6, 7, and 8. So between the two of them, when I combine these two together, I don't write the 7 twice. So I'll have 1, 3, 5, 6, and 8. Oh, sorry.
What?
I just had to think about what I just said.
Yeah.
1, 3, 5, 6, 7, and 8.
So 6.
Yeah, 6 will be in there. All right, so here's my situation from a visual perspective. I have 1, 3, 5, 7 on the one hand, and then I've got 6, 7, 8 on the other hand. You see how these two share a 7? Give me the collection that is, this is OR. What's shaded here is the OR situation. So what numbers are in there? I said, what I have shaded here is the OR. It illustrates the OR of these two, or the joining of these two. So tell me, what all numbers do I have in my collection? All these right here, how many is that? 6. So you got 6 of these numbers out of a total of 8. You could also, there's an OR equation. Do you remember that one? I'll draw it in the longest form possible. It's nice to be able to do things in more than one way. This requires you to be able to visualize, I guess, somewhat. Here's a secondary method. So I'll put the formula up here. Hopefully you can follow it. That's definitely a formula you want to have, you want to make sure that you have down. Because you can use that on this, it makes this, the formula will make the problem easier to do than the way I just did it. So what we do is this, break it up, I got the probability of it being odd, plus the probability that you're between 6 and 8.
So it might be easier, this will help you instead of trying to figure it out by looking at the numbers that are involved. This formula is meant to make life easier on you. So start with the first one here, this probability of being odd. What is that probability that you land on an odd number? 4 out of 8. Now, what did we say before for between 6 and 8 was 3 out of 8? Now, the and situation tends to be simpler for our brains to work with because you're working on a smaller collection. Now, what we want, I want you to tell me, give me an odd number between 6 and 8. How many, that's the only one, isn't there? 7 is the only odd number between 6 and 8. So there's only 1 out of 8 of those. And then when you add these all together, you just add along the numerators because they all have the same denominator. I have 4 plus 3 is 7 minus 1 is 6. Any questions? What I'm gonna do, anything that I give you, probably I'm not gonna be inventing new game, but the ones that we've discussed. So for example, cards, I could ask you about drawing a card from a deck. Make sure you bring your papers, just in case I get that feeling when I'm making this thing up. Draw a card. So if you know cards, of course, you don't need the cheat sheet, but you're perfectly able to use it if you'd like. Do this, give me the probability that that card is either red or a face card. Let's see, the probability has to be between 0 and 1. Not sure. Oh, you put, oh, I thought you wrote 100. You put that down. You might find the formula very helpful here. .1. Thank you. Test is on brace for it.
Anybody think they get it?
Yes. Piece of So there's the formula in action. The red cards, there's 26 of those. How many base cards are there? Well, 12 bases on those cards. Now, finally, how many of those base cards are red? 6. There's 12 base cards, half are red and half are black, right? And then just go along the tops. I have 26 plus 12 is 38, minus 6 is 32. Here's another one for you. Same style of problem. Find for me the probability of either a face or an ace card. Face or ace. But that's like a 8 or 13. But yeah, I ended up. It's. No, where am I? But that's part of the problem, you have to try to determine that.
All right, I'm gonna go according to this picture here. How many of these things are face cards? We just did that one. There's 12 of them. How many aces? 4 of them. How many aces are also face cards? 0. There's no such thing as an ace and a face card at the same time. So when you decide to use the formula, that little piece will be 0. So there's the formula in action again. Obviously, this formula is important. The probability of having a face card, we did that one, that's 12 out of 52. There are 4 aces in the deck. And then finally, there are no cards that are both an ace and a face at the same time. And so we get 16 out of 52. Question for you. What do they call it? This situation here where the probability is 0.
Oh,
There's a phrase for that. Brian is with mutually exclusive. Yeah, thank you.
I haven't heard of it.
So mutually exclusive is what face cards and ace cards are. And we give it a complicated sounding name, but it's pretty simple. They just don't have anything in common. So be prepared for either situation to arise on your test where you may or may not have something in common. It doesn't mean if there's nothing in common that you're not doing something correct. Either situation could happen. Let's go with this here. Most of the stuff here, outside of an or and and event, I'm not going to do a lot of, I don't see much in the way of asking you about terminology per se, other than that I'll use the terminology and I'll expect that you know what I mean when I use it. Let's grab, this is a good one to grab. This one has all sorts of things you can do with these.
Okay, that it is the amplitude probability. I'm going to sit down and do all these problems probably before you get them done, but as you get them done, ask me, come around and I'll come check them. These are I love these kinds of questions where you have to play with some of the formulas. formula for this. But I think that you could probably reason it out. Would it be, one's less than there, so. You remember what the words are for this thing? A, given that B is true. So if I'm gonna compute this probability, I'm already assuming I've already landed on a 1, 2, or 3. Roll a 1, 2, or 3, do you understand? I've already assumed that. Now just tell me what items in A satisfy that it's either 1, 2, or 3. What items in A are less than 4? Just 2. So this will be 1 out of 6. You can reason it out sort of like that. You can use the formula for it. So you can reason your way through it, or you can use the formula. But you're gonna have to be able to figure out what does the collection of A and a B look like? Do we have to do it anywhere?
Yeah.
Down here, what does A and a B look like? So I need the items that are common between A and the B. What does do A and B have in common? Just 2, that's it, right? Right. So A and B, that's just going to equal 1 solitary item. That's just gonna be number 2. So this way is gonna cause you a little more difficulty because the probability of this is gonna be a fraction. Now, you could certainly go to decimals, I don't care, if you want to avoid this horrible situation. B has 3 out of 6 items. Do you remember how this simplifies if you're gonna go this route? You go 1/6 times, you flip the bottom one upside down. And we end up with 1/3. If you would have gone to decimals, instead used decimals for this problem, you would have found a decimal of like 0.3 with 3's going off. So here's another formula that you want to make sure that you have, because it'll definitely be on there.
Try to do part F.
Which is similar to part E. Yeah, the bottom one, upside down, right? You take the reciprocal of the bottom one. Did you notice I made a mistake up there? 1/6 for that answer, that's wrong. Put 1/6 up there, but down there it's 1/3. Yeah, it is 1/3. It should be, you should not get 2 different answers for the same thing. I'm sure I was reasoning that there were 3 on that denominator, but not right, but I thought. Anybody try it? Pretty good. Yeah.
Is it 1/3?
I'll put F over here. So they want the probability of B, given that A was already true. One thing you could say to yourself, if I'm gonna do it just by reasoning and not a formula, how many items are inside of A? 3 items. So this denominator is gonna be 3. Now inside of there, look for items in B that are also in A for the top part of this. How many items do A and B share in common? Just the number 2, right? So they only have 1 item in common. So they only have 1 out of 3 in common. Or if you use the formula for it, B/A. We did this one up here. It doesn't matter what order you write that. That's still going to be 1 out of 6. And A is still going to be 3 out of 6. And it simplifies exactly the way the other one did. And if you want to avoid fractions, almost, I'm sure you can, if you want to, if you don't like them that much. Most people don't like them in real life. That's hard to believe. Most people don't like fractions, but we avoid them as much as possible. What would the set of A or B look like? So look at A, I know it's kind of buried there. Remember, A or B is combining the 2 of them together, but you don't write them with repeated items. So when I do this, I do it this way. I put all the items from A in there. And then I look through 3, and then I look through B. Are there any items in B that I haven't already accounted for yet? 1 and 3. 1 and 3. So what's the probability of A or B? 5 out of 6. So we know it's gonna be 5 out of 6 because you can count them. Let me do the formula just to show you it's gonna give you 5 out of 6. That's letter H. So do you remember were those items, they were what, even numbers? So what's the probability of A? 3 out of 6, right?
Was that A then, two?
No, I think, well, I gotta go back up there.
B was even, A was 2.
Let's see, A is 2, 4, 6. I don't know, I wouldn't use the letter A. See, that's a stupid notation for even numbers, don't you think?
Oh, yeah, I have.
Don't, if you're doing this for yourself, don't do something as so stupid as that. Give yourself the letters that are going to be useful to you. So A are the even ones and B are the ones less than 4. I admit B, you probably can't come up with a better name than that, but this one you could have. So there's 3 out of 6 even numbers. Then we also had 3 out of 6 here. Do they have anything in common? How many they have in common was 1? I mean, the number 2 was all they had in common, right? 3 plus 3 is 6, minus 1 gives us 5/6. As we got before.
By the way, I will post this paper as a PDF online, so you can match that with what I'm doing if you decide to watch the video. I've noticed, like, if you go and watch my video, I've noticed that it's really good for curing insomnia. So if you're not sleeping or something, crank up one of my videos and you're out like a light. At least if there's anything else. So you can see this is the kind of problem. I'll probably pull a bunch of stuff like this here. You know what I'm saying? All these things that make you comfortable with the form, things that connect the notation with the formulas, stuff like of that nature. So this is a perfectly good example here to pull from. Example 3.3. These, oh, you know what? Let's do some of these because the tables are another way of getting probabilities. I won't do all of them. I'll just do some of them. How appropriate. We've talked about this in this class. Perfect.
Oh, God.
So we have the distribution of a random sample of 100 individuals organized by gender and whether they are right or left-handed. All right, I have never in a million years thought to consider that you might be more apt to be left-handed if you're male or female. I never crossed my mind. But they have a bunch of questions in regard to this. I'm going to pick some of them to do, not all of them, because there's too many and we have more stuff to do. Now they have the answers here, so I'll put this so you know that you can go back and look up the answer to these if you decide to work these, because it'd be a perfect one to try to practice for the test. I didn't mean to do that. Put it right under here. Can you guys see that? I don't know how much bigger I can make it. Now this was an appropriately labeled problem. Do you see what they did here? All the letters are appropriate for what they're supposed to be here. So let's just, I don't want to spend a huge amount of time, but I want to remind you of some things. Any of these probabilities are very simple, like the probability of a male, do you know just to read at the end of the row? So the probability of being a male, well, you need to add, you need to put the total of these things. So if you're given a table like this, you need to put these things in there. And then down here is always the grand total, which we know to be 100. So let me just say that again. The probability of being male is 52 out of 100. So these you can read directly from there. What about the and? Where do you find an and at? So we want female and, so part F, for example, female and left-hander. Where would I find it? I'll do letter F. What's the probability of being female and left-handed? So that's this right here, right? 4 out of 100. And then the next one to go with it is I. What's the probability of F or L?
Isn't that the same thing?
No, one is and one is or, completely different. So in something like this, I would really, using the formula is gonna be by far the easiest way to do a problem like this. So typically, the problems that involve an and, you can look at the problem and write down the answer. But the or, you typically are going to use the formula. Once again, there's our formula. The probability of just being female, 48 out of 100. Then we have the probability of being a lefty. How many is that out of 100? 13 out of 100. And then we just did the one being female and left-handed. You simply look at the intersection between the row and the column. You 4 out of 100. So adding across the numerators, I get 61 minus 57 out of 100. This problem, that having a denominator of 100 is the most, has got to be the most desirable thing besides 1. Because if you wanted to convert to decimals, you just do at 0.57. Are there any questions about this? What else could we get here? Let me do J and L. You'll remember there were 52 males. Therefore, how many were female? What is this probability then? Yep, 48 out of 100 it is. This is an interesting point too. There's a question like, if I were to give you, what's the probability of either being male or female? It's like that, male or female. Do you need to do the formula to know what that answer is going to be? What is the answer going to be? What's the probability we're going to have a male or female? Well, we're 100%. You're going to get a, I should have said, so what's the probability you're going to get a human?
Oh, that's.
So you can get so involved in a formula that you completely forget just flat out to think sometimes. You gotta be careful on that. Because if you were to use the formula, when you get to the part here, you're gonna get like male and female. I hope you know that that's 0. This one, since we've done all the other ones with F and L, let's do part L, the probability of F / L. And once again, there's a couple of ways to do this. You can use the formula, which I'll write up. And that's divided by the probability of. We did somewhere up there, the probability of F and L, right? Where was it? F, that one right there. And the probability of being left-hander was what? 13 out of 100? 0.13. Oh, this is nice. This works out really nicely. That's just 4 out of 13. Because you have several of these kinds of problems using either the visual or the formula. Sometimes you have to use the formula, the visual won't be there. Sometimes you may not have the formula handy because you only have, I don't know about when you would not use the formula though. I can't think of that situation.
So what have we got here? Being able to have sample space, all those formulas, what two words are very important right now? Or an and, those two are extremely important. Complement, conditional probability, these are all the things we've talked about so far. What is the conditional probability? That's when you see something like A given B. That's called a conditional probability. The condition being that the thing after the bar is true. Independent and mutually exclusive. These are important. Independence has one of three different types of categories. I'll pull this into the discussion. So these will have problems here that I'll ask you if two things are actually independent. Some things you're expected to know it as well. Things like rolling a die over and over again. Flipping a coin over and over again. If I take a coin and I take a coin and a die and throw them both at the same time, those are independent. Whatever comes up on the one has no influence on the other one. I'll use this example. It's fine with me. Yeah, that was worthless. Let's grab some of these here. For a problem like number 40, they don't give you the probability of E and F, but they tell you practically everything else about them. So if you use what I would do with these things is I would use the formula and see what parts I can plug in and what parts I cannot. Now I'll see what I can plug in. What information can I plug in? I can put the probability for F. What is the probability of F? 0.5. Well, that's not what I want though up there. I want the probability of E and F. What's the probability they occur at the same, what do they have in common?
You know what that means? That means that E and F is the empty set. This thing right here tells us that E and F that's what mutually exclusive means. So therefore, what's the probability of this? No, 0. The probability of the empty set is 0, remember that? This answer is just going to be 0. I want you to make sense of it too. E and F are mutually exclusive events. So when I'm talking about the probability of E slash F, I'm asking you, what's the probability that E is true, given that F has already occurred? Well, since E and F have nothing in common, I can't talk about anything in E that has already occurred. We'll do, when we come back from break, we'll do the rest of these problems, okay? Go ahead and take 15. By what? Oh, yeah. I'll post it all. Yes, sir.
Where was that tutoring place they told, they came in here before?
Did you get they have, it's 1108. It's E, whatever the name of that building is over there, it's 1108. It's down in the basement.
Oh,
it's
it's
across-
on the other building.
It's across from the. Okay, no, wait, there's 2 places, I think. There's another one, on the other that I know about. That's 1108. I had to talk. And build up.
We could still review, right? We could still review. I hope the code is, right?
You probably would.
Okay. It's not a good check. Wait, can you send me it? Can you send it and I'll? Yes.
You have a school board.
Okay. Okay. I'm very up before you. Or I was pushing it. What's his name?
Me,
Yeah,
camera.
camera. I would say so, I'll be off. Or just check out your number. Oh. Two different terrified, one local and one is on the building. Hey, we don't want anything like opposition group that. Down here. Oh, out here.
I-
You can tell that I'm running the airport today, I'm just out of it. No, I don't know, we should have done this.
Sure.
I know, I was like. It's not. Is it terrible? No. No. Sure, I'm sorry.
Habit.
Oh, it was nice. Yeah, great.
I was joking, and then you said,
Yeah, correct.
okay. Literally, we clustered together, but and it was like,
I don't know what I'm gonna do. That was
I'm not gonna.
Instead of everything. I'm just copying.
I'm in the home.
Right into the line.
I did the last two.
I did something, and I'm really cheating because when I asked them to do one of the problems, I have the selfie that they need, so I'm like, no, let's. Chart, I could have sworn that forms about it, you like, the way you, the denominator was based on the way you rapidly fast, it wasn't all out of under. Thank you for that,
Yeah, one that.
no, there was one that wasn't like, where the denominator wasn't always out of under.
Oh, yeah.
I remember that one.
And then I was like, then what was that?
That's,
What was that?
I remember what you're talking about, we were like, the top one was like them, and the bottom was like,
They saw all of it. Yeah, they saw how they, later. And it was their jerseys and their layers. It was in the homework. Number to like 13. Okay. Oh, okay, it's wrong. Oh, that's why I gave the biggest thing. Well, if there's one that has not, I'm finding the answer and I figure out how they got it. Yeah, that's what I did on the holiday. But I'm not getting zero.
I'm not cheating.
A little bit later, so I'll turn around and maybe. You said 1:15.
Oh, I think it looks like without placement.
1:01 to 1:15. Oh, yeah, I did that. Cheating.
You can ask study group for real.
Please, no one change the name, but I thought it changed and all of that was. Yeah. I think it's gonna be there.
I'm off tomorrow, but then I have to go in on Saturday for the 2 hours and hope that weekend. I'm so mad.
It's this one, we're gonna do it. The denominator kind of which road the calendar looking at. Lost kid going to the worse. Well, one saw the, so we weren't supposed to do it, but this is like what. So what's the difference between this and the left thing?
It is.
The left.
Well, I understand that, but why would you tell me what I'm saying?
He said that all of those are out on the 10 week is going on, but the way we did this last week, they wouldn't all be out.
No, they wouldn't.
But I said out of like 44 or whatever, it wasn't. But now we literally just.
That's not all we did. I don't know.
Well, it was one of the graphs and like he was just on the
You
line.
can confuse yourself.
And now it's trying to be like,
This is like, let's see if we can get it right.
no, we didn't see where we were going to respond. I think not.
I didn't do that.
Oh my God, I'm gonna do something. Do you want to talk to you? I'll send you a phone for this. It's all blue anyway. I always have it on. So Dave, you're at home and I'm gonna give you a trouble. What do you do?
That's insane.
Yeah, but it's all what coffee? No, you can turn it off. I just always keep mine on. Remember that.
Scared still.
But you can make yourself like. So it's like the, let's say the ranking, the denominator was always 100. But last week when we did things like that, this was one of the homework problems, and they weren't always out of 100. What's the difference? Like when it's.
Well, they call it third of heartbeat, that's one. We can do this one, for the front 130.
Yeah.
No.
Yeah. But the calendar, not always the best.
What was that problem number?
In the homework,
13. Oh. The only problem that is related to what you're telling me is this last one. Right here, this given one.
Yeah.
So let's pull this in. Okay, let me buzz through this quickly so we have time to go to finish up, I hope.
People back.
If you're given a table, immediately start doing this if they don't do it for you. Oh, wait, there's one more now. It's 18:45. This way you can check yourself, to make sure that they both add up to the same thing. That's 9. All right, so I need 80, 106 it looks like. They didn't tell me it was 106, so let's see if this has a 68, 97, 106. Okay, so 106. So most of these will have 106 as the denominator. Except the last one won't. So I don't, man, they're pretty wordy in their things, aren't they? How wordy that is. So part E, we're discussing here, given that they weigh at most 210 pounds. So what's my denominator to be on part E? So at most 210 pounds, that's right here, 33. So the denominator would be 33. And then what do they have before? This is the vertical bar, by the way. Now, find the probability, so we've got 36. Find the probability. Find the probability that the shirt number is from 1 to 33, given that their weight is at most 210 pounds. So this is the column we're talking about for part E. How many in there have a shirt between 1 to 33? 21, yes. Now, I like to do things in the second way. I'm going to use the equation so you get the same thing. So I'm going to call all of this okay. That way I don't have to write all that stuff. So this is used in the formula. Let's see if we can figure out A and B. I'm still, can you figure out A and B? So we want, can you tell me all those people who have a shirt from 1 to 33 that's at most 210 pounds? What block are they talking about? That 21 block. So how many people are on this whole table? 106? It moved, it changed them, didn't it? And that was 21 out of 106. And the Bs was over there. At most 100, 210 pounds is this 33. And then when you put the bottom denominator, you'll notice that the 106s cancel out.
Anytime the denominator changes, we want to give it.
Yeah. All right, what have we covered so far? 3.1 and 3.2 are pretty heavy sections. 3.3, we've talked about 3.3. These are the two rules. We've talked about the addition and multiplication rules. Actually, we haven't discussed a lot of multiplication rules, so I will do that. Let me put these up there to remind you about them. The addition rule, we've done a bunch of those today. Let me put it up here. Personally, I wouldn't give it like they're doing. In fact, I'm going to delete that. I'm going to go back. I want a different part. I'm just going to do this one. There's no reason you don't need the other formula. This will work no matter what. So we've got one rule for addition. Was the multiplication rule in there? Oh, it's a, there it is. There's a couple of things that are important here. The multiplication rule, this is the one we've been using the whole time. This, can you guys see my mouse moving around here? You see what I'm talking about? That's the one we have been using. If this here, you can also use this one. So either one of these two formulas will be fine. And then here, if they so happen to be independent of each other, then you get something like this happening. I think we did a problem like this one. It's a perfectly good problem though, because it gives you all the things and it makes, it gives you just the information you need to do the problem. If I were them, if I were making up this problem, I would use the letter F in place of the letter A. Do you guys see what's going on there? They're allowing A to equal the event that he makes his first attempt. I would have called it F. I would have called B S. But I wouldn't have used the letter B for that. S seems more reasonable to me. What is the probability that he makes both goals? That means they want A and B to be true. So this little piece of information here. He makes the first goal, so we'll call that was A. So that's what that piece of information told you. You guys understand that? Okay, good. Now, the probability that he makes both goals, so they want A and B to be the case. There's two formulas for it. Now, you should have these two formulas handy on your paper as you're looking at this problem. Which one would I want to work with in this problem? Formula 1 or 2? Formula 2, because I'm given B/A, aren't I? So I noticed this is what they gave me. They gave me B/A. The only one here that fits the bill is this guy right here. So that thing equals the probability of B/A times the probability of A. What's the probability that they make the first throw? 0.65. Whatever that turns out to be. I get 0.5850. So the second question then is the probability of A or B. There's the formula for probability of A or B. The probability of A and B, or both of them, are 0.65. Now, keep in mind this, as I'm doing this problem, right now, this answer is adding up to be more than 1. That's not possible in a probability. That means there's got to be something between. That means I've got to have something that's at least, that'll bring that back down to less than 1. That's this guy right here. Are A and B independent? So that's what they're asking you. If this equation is true, then they're independent. If it's not true, they're not independent. So I'm just gonna fill in the numbers. We did the probability of A and B up here. Let's see if that is actually true. So what is your answer to this part C? The answer would be no. This is not equal. Are they mutually exclusive? No. Right. If they were mutually exclusive, this thing up here would have been zero. Or if they're mutually exclusive, they have no and. Their and is an empty set. So that is also no. And that's because
You don't have to do much in the way of manipulating equations, but you will need to be able to fill out all the blank spots. And you can see there's a lot of equations, so you're gonna want to get comfortable with those. I'd probably recommend redoing maybe these examples sometime this weekend without the benefit of me showing you. I just want to make sure there's nothing that I'm missing in here. Nope, we're good there, all these. Don't forget to, we talked about it a little bit, the complement of a set. Make sure you know that that's the one with the little prime. Make sure you know how to deal with the complement of a set. Contingency tables. Let's do one of these. I think I might have done this example, try it 320, so I'm going to try to do this one here. Do you guys remember what I did? Okay, so I'll do this one then. That way later on, if I don't do all of them, you can check out the answers later on. This one, they were kind enough to give us the totals in the table. These are really easy. I'm not going to use their notation.
I'm going to use letters instead. So we'll call this S, N, U, and D. So the first part says, find the probability the driver is a cell phone user. So uses, that means you, right? It's the probability of you. What is the probability of you? Out of how many? Right, out of 755. What's the probability of an N? Or how many N's are there? $685. out of a total of 75.
Okay, now, probability of no speeding. Or, yeah, no speeding violations, and they were a cell phone user. I should have put a U, not a D.
I'll say.
You gotta change that D to a U.
So all I gotta do is look for the intersection of column N and row U. How many is that?
280.
280 out of 755. You guys understand what we're doing here? But you're quiet, so sometimes I've been told that when, I told Susan before, when you're quiet, I actually think you know exactly what I mean. They told me that's not what that means. Well, so you're not gonna tell me what's wrong with it? I don't understand. So you're silent about it? Let's see, the next one is an OR problem. That is a driver is a self, so they are a U or N. Once again, we'll use the formula. Clearly, you would have had to have done this before you do this because this is inside of this formula. All right, probability of U, where was the U's, what, that was this, right? So that was 305 out of 755. Now, the N, the column is what, 685? And then we just did this one. That was 280 or 755. Notice this is going over 755, but when you subtract that off, it'll come back down. So let's say I've got 990 minus 280 would be 710.
Yeah.
And the problem is, I told you, I don't care what version, give me the answer decimal or fraction, just choose whatever's convenient for a given situation. Then we have these given situations. So that was D, this must be part of E. The probability that they are a cell phone user, so you, given that they had a violation in the last year. What do you call it, S?
Yeah.
Are we good? Let me pull this back in. See this thing. All right, so I'm using the formula P U slash S. This is what it is. It'll be easy to do that one. We need U and S. Where is it at? I hate the fact that if you do certain hand gestures, you're actually telling me you wanted to do something, and I did not intend it to do that. But anyways, what is it? Oh, U and S. Where is the U
And that's 25 over 755. This is the one where you're gonna get a new denominator. So now the probability of S, what is that? 70 slash 755. When it simplifies, it's just going to be this. 25 over 70. What was not a cell phone user? No, there's other ways. You could probably do it just by looking at the table. Yeah, they can do it that way. Well, because when you're doing it, you're just gonna look at only the S, is that a column?
Yeah.
Yeah, S, so you're only gonna look at that column, that's why you've got 60 down there. The next one. Is that probability that they had no violation. What was that? What was that? Really? To make sure I'm doing the right letters. No violations, where is that? That's what I'm using N. And then not a cell phone user, that's a D. Bam. So we're good there. Once again, I'll use the formula. And it's, if you can do it by just looking at the table, do it both ways. It's a good way to check yourself, doing it by just reasoning it out on the table. And you know what, as a matter of fact, let me do it that way, just so you can see how it works. So I won't bother with the formula here, just to show you that you can do it more than one way. So N slash D, we're assuming that D is already true. So if I'm assuming that D is already true, I'm talking about one of these 450, you understand? Some of those 450. So I already know down there is going to be 450. Now ask yourself, of those 450, how many of those were N? Of those 450, how many of those were N? 405. Question? Time is it? Okay, we have plenty of time. Here, we talked about probability distribution functions. I just want to put the table up here. I don't want to put anything more than that because there's a couple of things that you need to know about these. A probability distribution function or table is one where they list all the possible outcomes and the associated probabilities. So whatever's going on in this example, these are all the possibilities that X can be. So with that being said, then this side has to add up to a total of 100% or one, whatever way you want to look at it. So this one here, you'll notice, let's make sure it does. 4 plus 8 is 12. Plus 16 is 28. 42, 48, 50. So I do get 50 out of 50 or 1. distribution function, okay. Try to make this look like a circle if I can. So I just invented this on the spot. Pretend you're playing a game with a spinner. You spin the spinner once. Okay? So this is a game with spinners. Spin the spinner one time. What I want you to do is create the probability distribution table for it. Guess I could say compute. Probability distribution. So what are the things that you need in a probability distribution? You need all of the outcomes and you need all of their probabilities. So let's start with what are all the possible outcomes I can have here? What are they? You don't say 5 twice. This pretend this is a game. This is a game at, I don't know, Las Vegas or something like that. The game may be that like if you hit a 5, there's no payout, but you don't lose anything. You know, so you can keep playing. It may be something like that. I didn't think very hard about it when I made it up. The only possibilities are 1, 2, 3, 4, and 5. Can you give me the probabilities of each of these things? You can't have a probability bigger than 1.
It's 1/6 and 1/2.
Or you can do that, or you can do decimals. So if you look at this, it's not 1/6 either. This here, well, I mean, if there was a line in here, there'd be 8 spots. I don't know if I'd do that. Better yet, doesn't the 5s occupy 50% of the picture? That's the whole idea, that would be the easiest one to get on. So half of it is 0.5. With that being said, could you tell me what percentages or decimals the rest of them are going to be? So each wedge, each thing here is 0.25. So how much is half of that? 33. Well, let's try this again. This is 0.25, so I think you meant to say 0.125. So we're gonna have, and that's for all of these, right? All the rest of them are that. And you can check yourself by making sure that those decimals at the end add up to 1. You want to make sure that these always add up to 1. That way you know when you're done. You guys understand this? Very good. So I like this because you can look at the probability in terms of a visual. I like that, and that's available. What's another one that I'm probably gonna do? What I'll do is I'm gonna give you one after I do this one. It'll be about dealing with a bag of marbles. I always like to have those on test as well. Oh, yeah. Same example. All right, suppose you pay $1 to spin one time. If you get a 1, yeah, I'm gonna change this. We're gonna deal with adjustments. All right, suppose you play this game. I'm making it up on the spot, so I certainly hope it works out in the end. If you're playing this game, it's a weird game because you're only going to win $1 if you get 1, 2, or 3. If you happen to hit on 4, you will actually make money there. You'll get $15. And finally, if you do hit a 5, it's what they call a push. You don't have to pay anything, you get your money back. So question that we did here was, what's the expected value when you play these games? Now, see the way it's structured here, the game is reasonably created, I suppose, if I end up getting, if my expected value is negative, because any game that's going to make money, the average person has to lose money, the game, otherwise they won't have the game. So we look at all these situations, the way I do them is like this. All right, so what I put for X's, that's where I used how much it actually ended up costing. So in the first three outcomes, if you get 1, 2, or 3, you pay $10 to play and you only win $1. So how much did the game, how much did the game effectively cost you? $9. So that means you're gonna put a -9 here. This is also a -9, and so is this. Now, if you got a 4, though, you won. That's the only situation where you won was when you got a 4. What's your effective payout for number 4? How much money do you get if you win? If you hit a 4? No, you didn't pay a dollar.
$10.75.
Right, exactly. I indicate this with a +5 here. And then last but not least, the 5, if you get a 5, nothing. So this is the guy that's gonna tell me when you add this up, that's the expected value. That's the formula for the expected value, just add those numbers up. So on average, you're gonna lose $2.75 per game. So your expected value then, this is what you should write for your answer. You should use the appropriate formula, notation. So if you get one of these on a test and you somehow come up with a positive version of that, you should think twice about what's going on. It's not a reasonable game if that happens. Now, I should say something like this. That's how much you can expect to lose every time you play is $2.75. However, the gambling place, they expect to win exactly that amount every time you play. Do you know what I'm saying? Whatever's negative to you is positive to them. Let me give you one. I'll make one up here. Pink marble. Do they even make pink marbles? They do in my game. All right, so. All right, so there's your task. Reach and grab marble at random, create the probability distribution table. That's, what is that? That's what we just did last time. That's this guy up here. Create me one of these things. So you can do decimals or fractions. I really don't care what you use. Go ahead and use that to make the probability distribution. Do you guys get all these net numbers that I get? All right, now let's attach some dollars to it, make it a game, and compute the, expected value. So you're gonna draw one marble out of this bag. You're gonna pay $1 for that privilege, and I wanted to also, they always ask us to bring to bear in certain classes, critical thinking skills and whatnot. When you look at the probabilities associated with each of these outcomes here, what do you suppose is gonna have the lowest payout, if there is one? Blue, what would have the highest payout? Green. That's obvious, it's the way the game's structured. Blue, red, what else? Oh, wait, no, red, there's fewer red ones, aren't there? Red, where's that? Red, there was fewer red ones, so I'm gonna increase this here. Now, unless I don't, if I say nothing, you may not assume that you're getting your money back when you win, okay? That's not an assumption you can make unless I tell you that. If you, on the test day, you come up to me, or on the test day, you don't remember what my agreement here is, you can come and ask me, I will tell you what the deal is. So these things here, in case you don't like that version, that's the way they used to write 10 cents. You can write it this way if you prefer. So give me your expected value for this game. Times that 5.
running money, do we still keep it down like that?
Yeah, you can. It's just, this is, remember, this is just an average, so that kind of stuff can happen. Anybody get their expected value yet?
$200 somewhere. What I do when I make up my table is I allow X to be the dollar, the really about. In the payout for a blue one, what was the payout? 10 cents. Right, 90 cents, right, exactly right. So negative 0.90. Then how about if you get a red one? Negative 0.5, so that's negative 50 cents. How about green? When, so it's positive there. How about pink? Positive 4. So you need that and you need this. What was the probability of getting blue? There was 10 of them that were blue?
Yeah.
So 10 out of 23, right? And the next one, there were 7. Make sure that column adds up to 1. That way you know you've got all the costs, everything. I'm just gonna go all decimals on this last column. But I mean, basically, you know what this means, right? What you do to get this, you take this times this. And that's the column you want to add up. Is your expected value down here? So that's like, what is this? 15.22 cents. Look, it doesn't have to make sense. This is just an average. Nobody's getting paid out 15.22 cents. Over time, it averages that amount. So, but it is negative. That's the important thing, is that, you're going to be on average losing, and so the game is appropriately designed.
Here's a couple of formulas that we had for probability distribution. So these are the formulas you use. What in the world is that sound? Look, don't do that to me because I don't know if it's in here or out there. We have, these are the two things that we need, the mean and the standard deviation for a probability distribution. So here's a probability distribution I'm giving you. These are the formulas you want to use. And that first one, the mean there is exactly the same as the expected value. They are the same concept. What did you say? H. Mu, the Greek letter mu. Yeah, they go to the, we go, I know the Greek alphabet just being a mathematician. We even go to Hebrew alphabet when we need to. Oop, we're out of time. For the mean, I got 0.4 for the mean. You guys get that? 0.4? I'll do it up as soon as it's done here, but if you got these, you're free to go. I didn't realize at the time. For the standard deviation, I got 0.9165. If you got these numbers, head on out. For those that didn't, I'm gonna do these and you can check and see it where numbers are different from mine.
We're right.
Yes, I'm putting this on Blackboard. I'm gonna, this thing, that should come into my email tonight, so I didn't put that on Blackboard as well.
Does it matter if you add on the zeros?
No.
Okay, but I'll be doing it there.
And what did you say the textbook I'm covering again?
3 and 4, chapters 3 and 4.
Okay.
I hope I got video today. Let's cancel this.